So today we will be discussing the solvent-solute interactions as we said in the last class. The solvent-solute interactions is the mechanism by which a solution is formed. We know that for a successful formation of solution, there must be attraction between the solvent and the solute. The solvents, on the basis of their polarity, we classify into three types. Number one, the polar solvents. Number two, the semi-polars, and number three, the non-polars. The semi-polars are the intermediate solvents which have intermediate polarity and intermediate dipole moment and dielectric constant. The polar solvents have the highest dielectric constants, highest dipole moment and highest polarity. The non-polars being the weakest one, low dipole moment, low dielectric constant, low polarity. The examples of these categories of solvents: for polar solvents, it's water obviously. For semi-polars, these are the alcohols, acetone, then polyhydric alcohols like glycol, glycerols, etc. And non-polar ones are the organic solvents like benzene, toluene, etc. So, we will discuss the most important class of the solvents in today's class, that is polar solvents. As we know that in most of the pharmaceutical preparations, water is used in many preparations rather, it is used as a solvent, and so polar solvents forms the most important category of solvents for pharmaceuticals. So the mechanisms by which the polar solvents can dissolve typical types of solutes. The first is the high dipole moment of the polar solvents. Because of the high dipole moment of these polar solvents, they are capable of dissolving ionic and other polar solutes. Okay? So the salts which when dissolved in water they get ionized, these salts they can dissolve in water because of high dipole moment of water. We know the basic phenomena of solubility is like dissolves like. So owing to it, the ionic solutes and other polar solutes which have high dipole moment, they can dissolve in water to form a solution successfully. The second type of mechanism by which water can dissolve some typical solutes is formation of hydrogen bonds. While discussing the forces of attraction and repulsion, we have seen that in case of water molecule, the positively charged hydrogens, they can form bonds of attraction with the negatively charged species in many substances like sodium chloride, for example, or any other substance to which a hydrogen bond can be formed. These substances can be dissolved in water to form a solution successfully. This is because of the ability of water to form hydrogen bonds. Which are the solutes that can dissolve by this mechanism? Phenols, alcohols, aldehydes, ketones, amines and other oxy and nitrogen compounds. Okay? Fine. So, that is the second mechanism by which the polar solvents can dissolve these types of solutes. The third type of mechanism of these polar solvents to form a solution is sharing of electrons. So, based on the Lewis acid-base concept, that those solutes which can share a lone pair of electrons with water or the polar solvent, they can be dissolved because of on the basis of Lewis acid-base concept. The last consideration, so these are all the rough estimates of formation of solution. The high dipole moment, hydrogen bond, sharing of electrons. Apart from it, the structural features of the solute and the solvent, they play an important role in determining the solubility. In case of the solutes, the ratio of polar groups to non-polar groups, it is an important factor. If this ratio is high, that is the number of polar groups present are more, the water solubility increases and vice versa. Then if there is presence of additional polar groups in the solute, then it adds to the water solubility or it increases the ease of the solute to dissolve in water. We know polyhydric alcohols, they dissolve very easily in alcohol because of the additional OH groups that are present. Then the branching of carbon chain In case of the straight chain material, the solubility is lesser as compared to branch chain. So branching increases the aqueous solubility.